So the way that we can explain this is through something called electron promotion and hybridization of atomic orbitals. So let's take a look at what we mean by this. So if we take our carbon atom here, which has 2 electrons in the 2s orbital, and we promote one of these electrons into a 2p orbital, what we see now is that, yes, we have 4 unpaired electrons. So looking at this might not look so good to you. What we're proposing here is that you take a nice low energy s electron and move it into a higher energy p orbital. And the truth is that, yes, this costs energy. We're going up to a higher energy state. But it doesn't actually cost as much energy as you might think, because in this s orbital here, we have a paired electron situation where we're moving up to a p orbital where the electron is no longer paired, so it won't feel quite as much electron repulsion. But nonetheless, this is going to cost us energy, so we'll have to think about where that energy is going to come from, and we'll see that in just a minute. But let's assume that this is, in fact, going to happen. So now what we have is 4 unpaired electrons. That's great, but it's still not quite the picture we need, because actually all the electrons are not in equal orbitals. One's in an s orbital and 3 are in p. But what we need to remember is the fact that we're talking about electrons, which are waves. When we're talking about orbitals, we're talking about wave functions. So we can actually constructively and destructively combine these waves, these atomic orbitals, to make a hybrid. So if we go ahead and hybridize our p orbitals and our s orbitals, we'll switch from having these original orbitals to having something called hybrid orbitals. And hybrid orbitals are all going to be completely equal, and you'll notice that they're higher in energy than the s orbital and lower in energy than the p orbital. That should make sense because they come from combining s orbitals and p orbitals. And specifically, when we give them a name, it's very clear exactly which orbitals they come from combining. We're calling these sp3 orbitals. That's because they come from combining 1 s orbital and 3 p orbitals. You should never get the names of hybrid orbitals wrong, because it's very straightforward. If it has 1 s and 3 p's, we call it sp3. Naming doesn't always make sense in chemistry, so I like to point out this is a place where naming does make a lot of sense. All right, so let's consider our methane situation now that we have our hybrid orbitals. So I want to mention also, these are exactly equivalent. They're equivalent in energy. They're equivalent in shape. The only thing that is different about these orbitals is their orientation in space. So actually, first, let's take a look at how we got these orbitals. We got them from combining, again, 1 s orbital and the 3 p orbitals. If we hybridize these, what we end up seeing are these 4 hybrid orbitals. You'll notice the shape is the same. All that's different is their orientation. So essentially, each of these orbitals come from linear combinations of all of the original orbitals. And it's hard to picture exactly how that happens, but one that you can at least start to get an idea is if you think about combining the 2s and the 2pz here, which is not quite accurate because, of course, we're combining all of them, but it will just give you a little bit of an idea of shape. You can see if we combine the s with the top lobe of the p, they're going to constructively interfere because they have the same sign. So you see in the hybrid orbital, we actually have a larger lobe on top where they constructively interfered. If you compare the s orbital with the bottom lobe, these have a different sign, so they're going to destructively interfere. So what you see is actually a diminished lobe on the back part of this sp3 orbital. So sp3 orbitals always have one huge lobe and one really little lobe. A lot of times when people draw them, they even only draw the big lobe just to keep their paper looking nicer, but there is that little tiny lobe on the other side. All right, so in terms of sp3 hybrid orbitals, let's combine all 4 together on one axis, because this is what's going to happen in an sp3 carbon atom. So in this case, what would you say that the angle is here? Right, great. So we've achieved the angle that we observed, which is good, which is 109.5. So we can think about now doing bonding, and now we have 4 equal orbitals with 1 electron each. So we can bring in 4 hydrogen atoms, which will each contribute another unpaired electron. So now what we have is 4 bonds. And we can think about where we did get that energy for electron promotion that I mentioned before, where we move the electron from the 2s to the 2p. We get that from bonding. We're going to release a lot of energy for bonding. It's going to more than make up for the fact that we actually had to spend some energy to promote that electron. So we can think about now, how do we describe this bond in valence bond theory? So the way that you describe a bond is you describe the orbitals that the bond comes from and also the symmetry of the bond. So would you expect this to be a pi bond or a sigma bond here? Okay, I'm hearing some mixed answers. It turns out that it's a sigma bond. The reason it's a sigma bond is because the sp3 hybrid orbital is directly interacting with the 1s orbital of the hydrogen atom, and that's going to happen on the internuclear axis. They're just coming together. Anytime two orbitals come straight on together in that internuclear axis, you're going to have a sigma bond. So if we go ahead and name this bond, what we're going to name it is sigma, because that's basically the shape of the bond, or that's how our bond is coming together. And then we're going to name the atomic orbitals that make it up. And it's being made up of a carbon 2sp3 orbital and a hydrogen 1s orbital.